awesome and giving me some good nights fairly close together, so I'm pretty excited. So I figure as much as I can get out, I will. So tonight, we're going to try to keep this one relatively short. To be honest with you, I really didn't plan for a night of broadcasting, but it was just such a beautiful night that I figured I would go ahead and do one kind of impromptu. So, what we're going to do tonight, the title of this one, if you notice, is The Death of a Star. So, what we're going to do is take a look at just four targets tonight, nothing long. Um, and we're going to look at exactly what it sounds like, the death of stars. So I started with our first one here. This is really kind of the showpiece, but it's going to be going behind some trees here before too long where I'm at, so I wanted to go ahead and get it covered. This here is the Crab Nebula, and it happens to be Messier 1. So it is the number one on Messier's list of objects. So Crab Nebula is about 6.2 thousand light years away, so 6,200 light years away, and it is fairly large. Obviously, it's going to be fairly large. Um, the What it actually is, of course, is a supernova remnant. So, um, again, I didn't take my normal notes that I would normally have off to my side, but I can tell you it is a supernova remnant. So, what does that mean for anybody that's watching who may not know? It is the death of a massive star. So, a star like Betelgeuse. So, if we were lucky enough to see Betelgeuse meet its demise and go supernova, then this is what we would end up with. The result years later would be this type of formation. So what happens? You get these supermassive stars, and really all stars, they all kind of go through the same sequence. It's just a matter of how large they are, kind of what they end up creating when they do kind of implode slash explode. So what you end up seeing is that the internal core has used up all of its material. All of that hydrogen material that it is fusing together has been converted to helium. So it's no longer creating heat, it's no longer doing anything on the inside, and when it does that, it loses pressure basically inside. Part of the equilibrium of a star is the pressure created by that reaction in its core. So it eventually starts to shrink and collapse in on itself, and become denser. Well, the falling of those materials and the rubbing that's created by them, pulling in and drawing in and getting closer together, the outer shells, there is hydrogen in those outer shells that wasn't going through the reaction because it wasn't in the core. So what you end up with is a kind of sort of an external explosion, and it blows off. As soon as that stuff gets hot enough, it'll essentially ignite, and it will blow off a portion of that outer shell. It will go through some more reactions. It will shrink in some more, and eventually, boom, it'll blow off more. And eventually, what happens is it blows off all of the actively burnable hydrogen and helium that's been fused into other compounds, and then it blows off in this violent reaction. So what you end up with is a neutron star, which often becomes a pulsar, and then this shell or cloud of all these ionized gases that have been blown off. Typically, you'll see nitrogen, you'll see oxygen, you maybe see carbon monoxide. There's all kinds of things that are created, all the way into heavy metals, depending on how violent some of the reactions are. Alright, and here we are at our next target. So I am going to go ahead and set this. This is in our preview mode here. I'm going to stop this and go ahead and put it in our stacking mode. Cut our exposure time down quite a bit. This is actually, as you can tell, is fairly bright. And I think you can probably tell what object it is we're looking at there. It is this one is called the Eskimo Nebula, or the Clown Face Nebula. Its identifier is actually NGC 2392, and this was discovered by William Herschel in 1787. So he found this little blob and said, "Wow, that's kind of weird. Worth recording." And so they noted it down. Yeah, we're gonna have to really cut our highlights down here so you can really kind of see what's going on here. So what we have here is it is a planetary nebula. So what is a planetary nebula? And I apologize for the music. My neighbor has come home, decided he needs to play his music loud enough for the neighborhood to hear. So a planetary nebula is another form of the death of a star. So typically your large supermassive stars like Betelgeuse are going to turn into supernova remnants, but your smaller stars, and they have determined that it's one solar mass or below, are typically going to create planetary nebulas. So what happens is they named it a planetary nebula, obviously, because it's very round. Most of them are very round. They appear to be some form of, let me get my stacking turned on here. They appear to be a planet, and so that's where they got their name from. But they are, of course, they're the death of a star. And I think what you can see here, and we can zoom it in a little bit. We won't get great detail out of it. I wish we could, but what you see here is this very bright inner core, which is an inner shell of blown off material that was blown off secondarily, and then this outer fainter shell that has been blown out previously. And as I said with the Crab Nebula, that's the pattern you typically see, is that they may have layered shells where they've blown out some material. It's kind of moved its way off into space, and they blow off a second round of material before they finally reach that neutron star stage. And so what we have, it's about 4,200 light years away, and for being what is the remnants of a star, it's extremely bright. I think we can agree on that. And so, yeah, so it's really, and as I do in other videos, I encourage you to go and take a look at this one on the Hubble Space Telescope site. It is far more impressive when you see a Hubble image of it, because it really, the reason they named it the Clown Face Nebula or the Eskimo Nebula is just based on what it looks like internally. That internal shell with the big, or the kind of bright neutron star in the middle looks sort of like a clown face to me, honestly. And then you've got almost what looks kind of like a clown, a ruffled collar on a clown. That's the outer shell. And I think what's really nice here is I'm looking at this Hubble telescope image that's on here, and what you can see in the Hubble is this really pronounced brighter section of material, and the fact that we've picked up that material is actually really nice. I'm really happy that we actually got that much detail out of it. And I think if I shortened my exposures and did a lot of stacks, we could actually probably catch more detail here in the center. But this does enough to give us what we want, and it's typically very hard to register the neutron star in the middle of these. So I think this is actually giving us a very good look at this particular planetary nebula, and a lot of them are. This is how they're going to look. They are not. I would say they're not super exciting, except for the fact they are. They're kind of one of my favorite objects because they're fun to find. Some of them are so small that you really can almost mistake them for a star, except the vast majority have a greenish blue hue to them, so they're kind of easy to tell. They're a little too round for a star. They don't have these diffraction lines that come off the stars. They tend to be a little more just roundish. So yeah, alright, we'll move on to our next target here, and I will see you there. Reason being is because this is one of the first things that I truly successfully imaged. I think it was probably one of the first, I guess you could say, difficult targets I successfully imaged. I was really pleased with it. It's not difficult because it's particularly bright. It's just that it's difficult to kind of squeeze that detail out of. And so I was really pleased with the fact I was able to get it, and it is honestly a very neat looking planetary nebula. So this one is NGC 3242, and it is known as the Ghost of Jupiter Nebula. And the reason being is because if you can squeeze out the detail, which is very difficult, it's because it's super bright in the middle. There we go. We're just going to turn those highlights way down. This is what you come out with. It's also kind of laughingly called the CBS Eye Nebula as well, because it looks like the CBS Eye on TV. And it is, there we go, that's really good right there. That gives us a good dim version of it. So what we have here, it is going to be about 3,600 light years away. Obviously it's another very bright planetary nebula, so it kind of bleeds out really easily. But it is again just another of these interesting nebulas. It was found by William Herschel again in 1785, and I think what's interesting here and what we can do here by cutting those highlights down really well is that this, at the end of the finger, is the neutron star at the center of this object. So that to me is super exciting. It's a little bloated, a little more bloated than it would be. It would typically be a finer point than that, but that is in fact the neutron star at the center of this nebula. So now if I cut these highlights back up, what we get kind of blows that out, but what we should see, I'll throw these midtones way up. Let's see, let's try that. Let's cut these midtones way out, highlights way down. There we go. So what we get is actually a really good view here of the structure of this nebula. There's not a lot of, I mean, there is, if you get a Hubble image of it, of course there's some tendrils and things that you can see in this inner core, but that's not something we're going to be able to pick up, of course, in a smaller scope like we've got. But what we can see is the greater structure of this object. We've got this perfect circular outer shell of fainter gas and material, and then you've got of course this odd pupil-esque or iris-esque looking inner shell of material, and then of course your neutron star. And now I don't want to put my foot in my mouth on this one, but I believe when I've done some reading on this object in particular, there are actually jets of material that are that you can't see. I believe they're in the infrared, but there are these jets of material that are firing out of each end here, kind of off the corners of that eye-looking structure. And so neutron stars, I mentioned earlier, they become pulsars eventually, typically pretty quickly. So what that is basically as these neutron stars condense and they get tighter and tighter down on themselves, they begin to spin faster. So much like you would see a figure skater skating, they throw their leg out straight, it slows their spin down, they tuck their leg in, they get more dense, right? They're more concentrated and they spin faster. And that's what happens with these neutron stars. And as they spin, many of them eject out, they fire out basically streams of radio waves off the tops, off of two of their poles. And their poles don't always match their spin axis. So what can happen is these neutron stars, and the way we detect these neutron stars, these pulsars, often is they will shoot these beams of radio waves at Earth, and we pick them up on radio telescopes. So anyways, this, I could probably look deeper into it, and I'm sure there are probably this has probably been picked up on radio, but not necessarily, because if those beams are facing away from Earth, there's no radio waves for us to pick up. But there's potential maybe we pick up gamma rays that come off of them, which is high energy radioactive, I guess, nuclear waves, if you will. But nonetheless, yeah. So, anyways, another very cool one. This one's just such a cool one to look at. It's so nice to be able to pull that structure out and really see what it looks like. So, with that, we will move on to our last target. Our last one is going to be our faintest target of the night, and we are going to do our best to pull the detail out. It takes a bit. I've imaged it, and it takes a lot to image it. So, we will pull as much detail as we can, and just kind of talk about it. All right, I'll see you there. Restart this one. This one's for some reason going weird. And the reason being, if you see the Hubble image of it, you can kind of see that center structure coming down an owl's face. But it is and begun to kind of blend. Thing here is that we are able to pick up, and probably due to the fact that the outer shell has started to fade some and is cooling and spreading, is that it really leaves this neutron star easy to observe. You can see that blue dot right there in the middle. That is that super compressed neutron star that's in there in the middle, and more than likely a pulsar at this time. And the really cool thing with those pulsars is that they can spin hundreds of times a second. So spinning super fast. And the only thing that really keeps them together is the fact that they are so densely held together by all of that gravity, because of all that matter compressed. I think there was some figures I saw, just some fun figures. They said basically if you could take a teaspoon of a neutron star, it would weigh something like 1 million tons or something like that. So it's just so super compressed that it's actually forcing the nuclei of these these things to merge together. So yeah. So anyways, that's like I said, that's going to wrap it up. There's not a lot more detail that pulls out of this. I think we'd have to leave it running for a fairly long exposure. And for some reason, I'm getting a lot of kind of noise readout in here for some reason on this image. And so the stacking's not really taking care of that. But nonetheless, as I said, take all of these objects we've looked at tonight, go look at them in Hubble, read about them online. There's so much more information than I can tell you, but I really do enjoy trying to find some of these planetary nebulae and trying to look at them. They're really interesting objects. I think, to me, the most exciting part is realizing that what you are looking at when you see these is the death of an object that is millions, perhaps billions of years old. And that to me is just kind of an amazing thing to see, and to be able to see that as not as it's occurring, it's already occurred, but you're able to see that result of it, and that to me is very amazing. So with that, this is Astronomonkey signing off. Please